Here we're going to use this very nice diagram from the textbook on igneous and metamorphic petrology from John Winter to explain the binary eutectic. It is binary because we have just two components, diopside and anorthite. It is a eutectic that refers to this geometry here in terms of the phase boundaries, in large part because diopside and anorthite have almost no solid solution. Here we're going to treat them as if they have zero solid solution. So molecules of anorthite will not dissolve into diopside, and molecules of diopside will not dissolve into anorthite. And so now let's take a look at the phase relationships. We have at very cold temperatures a rock in this system that would be made of two minerals, diopside and anorthite, and the amount of those minerals would vary depending on what the bulk composition is. So let's take one of these guys here. If we had a bulk composition that fell here, then since we're looking at the weight percent of anorthite, then if we measured out the weight of the minerals, if we took this rock, this mixture of pyroxene and plagioclase, 80% by weight of the material would be plagioclase of anorthite composition, and 20% would be diopside. On the other hand, if we took something that was over here, a bulk composition there, if we broke apart the minerals into separate piles and weighed them, then 30% of the material would be anorthite, and 70% would be diopside. Right, so what happens if we have pure diopside over here? Well, we don't really need this. We've got the scale bar here. Pure diopside will melt at 1392 degrees centigrade. Pure anorthite will melt over here at a much higher temperature, 1553. Let's take a case of melting, and we're just going to focus on melting in this diagram. If we had something that was a mixture of 80% anorthite and diopside. Now we don't have solid solution, we have separate minerals of diopside and anorthite. And in another video we'll talk about melting on grain boundaries, but if we have minerals of diopside and anorthite that are touching one another, then we would have the case where a film of melt would form at the grain boundary as we heat this material up. So we start out at very low temperatures down here, we take this composition and heat it up, and then when this rock reaches 1274, that's when the first liquid begins. What kind of liquid do we get? We get a liquid that is equal to the eutectic composition that is right there where these two liquidus curves, the anorthite plus liquid, liquidus, and the diopside plus liquid, liquidus meet. And they meet at a temperature of 1274 and a composition of about 42 weight percent anorthite. So notice that the liquid has a composition that in this case is much more diopside rich than the rock. So the rock has 80% anorthite, 80% anorthite crystals, but as we begin melting it, the melt that forms on the grain boundaries is going to be a film that has much less anorthite, much more diopside component in it. The one way to think about that is that if you have two minerals in contact, the interface is going to eat away much more quickly at the diopside crystal than at the anorthite crystal. But we'll again focus on that in a different video. Here we just want to interpret this diagram. What happens if we continue melting? Well, this is a very odd thing. As we pump heat into the system, we're going to maintain this temperature of 1274 until all of one of these two minerals disappears. And we can always tell which mineral will disappear first as we look at the up temperature range on this bulk composition. We're going to go from a solid diopside plus anorthite into an anorthite plus liquid field. That means diopside is gone. So we're going to sit there and add heat. All of the heat will go into melting diopside, well, actually a mixture of diopside and anorthite, until all of the diopside is gone. Once all the diopside is gone, all we have left is anorthite plus liquid. So now we'll enter the anorthite plus liquid field. Let's use our other vertical bar. So we're sitting here at 1274. Once all the diopside is gone, now we start moving up temperature, and we can pick any arbitrary temperature here. Let's pick a temperature of 1400 and take a look at what's going on. By the time the system has reached 1400 degrees, we have a mixture of anorthite plus liquid All of the diopside crystals are gone. They exist in terms of their composition only in the liquid state. We have, well, these levers aren't quite equal. We have, if we look at this total lever, this total bar from the liquidus point all the way out to the sideline, at 1400 degrees, it's almost cut in half. So we have about almost a 50-50 mixture of liquid and crystals. But as we go further and further up, take a look at how this part of the lever remains fixed, but it's proportionally a larger and larger fraction of this total distance. And by the time we hit this temperature here, this right-hand side of the lever is now the entirety of that lever, which was not true when we were down here. So that's the point at which we are 100% liquid. Again, we'll take a look at the lever rule in a different video. Here we're at 100% liquid, and that happens at about 1500 degrees. If we continue adding heat, then we just have a liquid and no other phases. The crystals are all gone, and that liquid simply becomes hotter, and we would move upward on that path. Let's take a look at melting of something that is over on this side of the eutectic. Well, actually, let's take a look at something that's over here. So here's 50% anorthite. What if you thought that anorthite was the last crystal to melt, only because it was in the majority, 80% anorthite, this part of the diagram shows that it's wrong. Over here, the way I've selected this bulk composition, let's get this out of the way. So here's our bulk composition here at 45 weight percent, about as close as I can get it to 45 weight percent anorthite. So that means this bulk composition is mostly diopside. It's 55 weight percent diopside. As we begin heating this rock, the rock will get hotter and hotter until we reach a temperature of 1274. But at 1274, we're still on the right-hand side, the anorthite-rich side of this eutectic point there. And so that means, even though diopside is the majority of the rock, the liquid will eat away at the diopside until the diopside is completely gone. How do we know? If we just simply follow this bulk composition upwards, eventually, again, we're going to hit the anorthite plus liquid field. So it doesn't matter which mineral is more abundant. What really matters is as you follow this bulk composition up, what is the sequence? And we go from diopside plus anorthite into anorthite plus liquid. That means diopside has to disappear, and the system will be entirely liquid at about whenever that temperature is there. It looks like it's 1300 degrees centigrade. Let's pick something over here. Let's say we have something that is only 10% anorthite and 90% diopside. We will take this rock, heat it upwards until we reach the eutectic temperature of 1274. So we'll be sitting there at a temperature of 1274. Because we are on the left side of this eutectic, we're going to enter that diopside plus liquid field. We can only do that by melting out all of the anorthite first. There's only 10% anorthite we need to get rid of. So again, here's the tricky part. We will add heat, but the temperature will not increase. It'll stay fixed at 1274, and all of the thermal energy will go into dissolving these minerals, melting them, converting them into liquid. And it'll do that until one of the minerals is gone. In this case, the first mineral to disappear is anorthite. We'll enter the diopside plus liquid field at some temperature above 1274. And now you can take a look at the levers. This side of the lever gives the amount of diopside. This one gives us the amount of liquid. And as we move upwards in temperature, this liquid side remains fixed, but you could see that the crystalline side is beginning to disappear. And we're at 100% liquid here at a temperature that is about 1375 degrees. Here's 1350 is right about that hash mark. There's 1400, about halfway in between, so about 1375. So these are examples of melting in the eutectic system, diopside plus anorthite.